Here we continue on our journey into continuity. So let's check out what this problem says. Graph and discuss the continuity of the function. Identify any discontinuities and the x values at which they occur. Well, that's pretty beefy. So let's start with the first part. Graph and discuss the continuity of the function. So these are just going to be rough sketches I'm going to be doing here. They're not perfect by any stretch. So we're just kind of sketching out sine looks something like this, right? Not the most perfect graph by any stretch. But the idea is that you're able to understand the basic concept here. So are there any discontinuities on here? So to discuss the continuities, to really ask, where are there any breaks, right? Any holes, jumps, or gaps? And there are none in sine. Sine goes on and on and on forever without any jumps, holes, or gaps. So discussing the continuity, I would say that we are continuous over all real numbers. So you could say over the reals or on negative infinity to infinity, however your teacher wants you to express real numbers. So it's continuous everywhere. Enough said. On to the next one. It's that simple. It's not so bad. Graph and discuss the continuity of this function. Identify any discontinuities and the x values at which they occur. Let's do it. So 1 over x plus 1, we've got a vertical asymptote at x equals -1 because that's where our denominator equals 0. So I'll say VA at x equals -1. So I'm going to just kind of lightly sketch that thing in there. So we've got your vertical asymptote. And what does this graph generally look like? Well, it roughly looks like this. And if you have trouble with graphing, it's okay with this exercise to use a graphing calculator or an awesome website like desmos.com, DESMOS.com, to check out what the graph looks like. Now, if you take a look at this, we have a continuous function almost everywhere. So you're traveling along here, we're continuous, we got no holes, jumps, or gaps, and oh no, there's a gap right there. So we have a, what I would call a non-removable discontinuity. So a non-removable, I probably just spelled that wrong. We're going to spell it without an E. Let's go for it. A non-removable discontinuity at x equals -1. And it's a vertical asymptote if you really need to be detailed. So we've discussed the x value at which that occurs, and actually by doing the second part first, we can then figure out what interval over which we're continuous. So we are continuous on, and I'm just going to abbreviate here, continuous over everywhere from -infinity to -1, so -infinity to -1, united with -1 to infinity. So we only have that slight interruption of a vertical asymptote at x equals -1. It is non-removable. On to the next one. That's it. Not bad, right? Graph and discuss the continuity of this function. Identify any discontinuities and the x values at which they occur. Now, to do this problem justice, what I'd like to do is factor it out first. Notice that the numerator factors to x minus 2 times x plus 2. The x minus 2's will divide out. Now, that alone allows us to say that the function is x plus 2 except x can't equal 2. And the reason why it can't equal 2 is in the original function, you would have gotten 0 over 0 at 2. It's indeterminate. So there's a hole or removable discontinuity. How about that? Removable discontinuity at x equals 2. That's where that hole is. Now the question is, what is the y value of that hole? We'll just plug 2 into x plus 2 to find out. 2 plus 2 equals 4. So it's at the point 2, 4 that we have the hole. So let's graph this thing out. X plus 2, we know has a y-intercept of 2. And then we go up 1 over 1. Up 1, ooh, not so fast, over 1, but there's a hole there. And then we keep on going like so. And I'm going to sketch in what will probably amount to be a pretty shoddy looking graph, but it'll do the trick. I'm not very good at freehanding a straight line. Good thing I'm a math teacher. So looking at this, now you've got a removable discontinuity there. Remember, a hole could be plugged, quote unquote. So what that means is if we were to plug that hole, we would be continuous on the curve. So a removable discontinuity exists at x equals 2. It is a hole. And we are continuous, so I'll say continuous everywhere except at x equals 2. That's it. We could have said the same for the last problem. We could have said we're continuous everywhere except at x equals -1, but I thought let's be fancy. Let's use some interval notation. And we did. So let's keep rocking it. Last one in the video. Graph and discuss the continuity of the function. By now you've memorized these directions. You might be like going to sleep at night, graph and discuss the continuity. Like, I hope you're not having dreams about this stuff. I dream of calculus, but that's not for everyone. Anyway, you got to memorize by now. So let's graph it out. So we've got the piecewise function. And so that piecewise function is going to be a line starting at -2, -2. That's just plugging in the -2 there. So that's going to be a hole here at -2, -2. And that'll be a line with a slope of 1. And I know to go in this direction because, again, it's all x values less than -2. Boom. Okay. Now, I'm going to start off where we left off. I'm going to plug in -2 here. That gets me 4 minus 6 is -2. So we're at the point -2, -2. So that essentially fills the hole here. And then we've got the parabola. And again, we're just doing a rough sketch here. We know that the vertex is going to be at -6. And we can go all symmetric on this thing and just get a rough graph of this thing going on like that. So the fact that we filled the hole there means that we're actually continuous everywhere. There are no holes, no jumps, and no gaps. So we are continuous over all real numbers. And again, there's multiple ways that we can express that, as I showed in problem number 1. Thought that R was a little crazy. That's it, y'all. That's how we discuss continuity. It's about looking for where we have discontinuities. And then everywhere else we don't have discontinuities, that's where we're continuous. Sweet stuff.